In this video, we will use an Excel model to demonstrate the use of the resampling or Monte Carlo analysis. We will look at the method for calculating the p-values for the goodness of fit chi-squared test when we only have small observed numbers in each category. In this example, we have 4 genotypes in which we expect to see observation numbers in the ratio of 9 to 3 to 3 to 1, and our actually observed numbers are 7, 8, 3 and 2. We wish to test whether the observed numbers could have occurred by chance, with the probabilities defined by these expected ratios. We first of all convert these expected ratios into expected proportions, such that the total of all the proportions adds up to 1. So to do this, for the first category, we must take the proportion of 9 as a ratio of the total of all the ratios, which is then the sum of all these ratios, and we will copy this formula down to do the same calculation for all of the categories. So we will put a $ in front of the references for B3 and B6 to define a constant range when we copy the formula. So 9 out of a total of 16 becomes a proportion of 0.5625, and if we copy this down, we will find equivalent proportions for each category adding up to a total of 1. With this information, we now wish to calculate the expected numbers we would observe given these proportions. So we must first enter the total number of observed events. So this is equal to the sum of all the observed values, giving a total number of observations of 20. So our expectation for the first category will be the total number of observations, but observed with the expected proportion of 0.5625 in C3, giving expected numbers for the first category of 11.25. We can copy this formula down to calculate expected numbers for all the categories, but again we will put a $ in this instance in front of the 7 to lock the total number of observations. We copy this down, and now we get expected numbers. Note that expected numbers in the chi-squared test do not have to be integer. They are just theoretical calculations, whereas of course observed numbers must be integer. We can now calculate the chi-squared goodness of fit statistic, which is equal to the sum of 4 chi-squared components, 1 from each category. So for the first category, it is the observed number in D3 minus the expected number in E3, and that difference squared, and then divided by the expected number in E3. And that calculation is repeated for each of the 4 categories, giving a total chi-squared statistic of 7.022. Now, for the purpose of the hypothesis test, we have to start with the null hypothesis that we have a set of observed numbers which have been randomly selected with probabilities based on the expected ratios of 9 to 3 to 3 to 1, and to calculate the proportion of those randomly selected null hypothesis values which give a chi-squared statistic equal to 7.022 or greater. And we will generate such a random sample in column G. And to start with the first category, we have to make a random selection from a total of 20 based on an expected probability of 0.5625, and this will be given by the binomial distribution, which we will enter as equal binomial, and we will use the binomial inverse function, where the number of trials is the total number of observations 20. The probability for this first category is the expected proportion in C3, and we wish to make a random selection based on this probability, so we will use the random function in Excel, giving in this case a random selection of 6, but each time we enter a new value into the spreadsheet, or every time we press the function key F9, we can generate a new randomly selected value. We will be copying this formula to other columns, so we will put a $sign in front of the C reference for the expected proportions to lock the reference to these proportions. The calculation of randomly selected values for the second category actually depends on how many observations are left to be selected after, in this case, 9 have been selected for the first category. So the formula for the second category is again using the binomial inverse function, but this time the numbers of possible values, the number of trials in this case, is the total number 20 minus whatever value we have in G3. So that gives the total number of trials in this case. And now the probability here is the probability for this specific category in C4, which is 0.1875, but then as a ratio of the total probabilities left for the remaining 3 categories. So that is the sum of C4 to C6, again performed with a random selection. Given 10 observed in the first category, a random selection with these probabilities of what is left is 3. We enter a similar formula in the next category, in that the number of trials, or the observations, is the total number of 20 in D7 minus the values that have already appeared in G3 and G4. So it's 20 minus 10 minus 5. And the probability then for this particular category is the specific probability of 0.1875, but then as a ratio of the probabilities for the remaining 2 categories, again with a random value. And for the final category, out of a total of 20 possible observations, we have already seen 9, 3 and 7 giving a total of 19, so that there would then be 1 observation left for the last category, and we can enter this as a formula as being equal to the total number of observations, but then minus the sum of all the previous observations. In this case now, after 8, 5 and 5 giving 18, there is just left 2 in the final category. Again, we will be copying this formula to other columns, so we will lock the reference to the total by putting a $, in front of the D for the total number of observations, and then we can enter. We can calculate the chi-squared value for this particular set of null hypothesis randomly selected data just by copying this formula. And for this new set of data, as we did that, this gives a chi-squared value of 1.33, and as we select new random data, we see that we get resampled chi-squared values, most of which are less than our value of 7.022, except that occasionally the null hypothesis will give a chi-squared value of greater than our observed experimental value. And for this data, if we were to reject the null hypothesis in this case, we would be making a type 1 error. And it is the proportion of type 1 errors for an infinite number of random selections that will give our p-value. And to test whether we have a type 1 error, we will enter under comparison an if test to test whether the resampled value is greater than or equal to our experimental value of 7.022. And this if function quite simply says if, and the logical test is whether the resampled value is either greater than or equal to the experimental value, and if it is, we will record a 1 for a type 1 error, otherwise we record a 0. Again, we want to lock references to the experimental value in D8 by putting $, in front of the D, and so for a resampled value of 1.867, this is less than 7.022, our comparison records a 0. There is not a type 1 error. However, repeating the tests, a chi-squared value of greater than 7 will record a 1, a type 1 error. We now choose to repeat this random test 10,000 times, but to save wear and tear on my computer's F9 button, we will copy this same calculation to a total of 10,000 columns. So we will go from column G to column NTV, giving a total of 10,000 random selections and calculations of the relevant chi-squared statistic. And we see that sample 9,994 gave a type 1 error. We can now return to the earlier columns. We now need to calculate the proportion of our 10,000 sampled values that gave a type 1 error. And we can do this just by taking the sum of all the values in this comparison row from G9 through to NTV9 as giving the total number of all the ones, but divide by the total number of trials of 10,000, giving a proportion in this case of 0.087. So this is the proportion of random trials using a null hypothesis which would return a type 1 error. So this proportion is then our p-value for the analysis. We also want to know the uncertainty in this p-value, and we can do that by using the formula for the standard deviation in a randomly selected proportion, which is equal to the square root of that proportion multiplied by 1 minus the proportion, and then divided by the total number of trials, which will be 10,000 in this case, giving a standard deviation uncertainty in this p-value of 0.0027. We now wish to calculate a confidence interval range for our best estimate of the p-value, and we will choose a 99% confidence interval, which then will be equal to the best estimate p-value, and the lower end of the confidence interval range will then be minus, and we multiply by the value of 2.58 to turn the standard deviation into a confidence deviation, giving a lower value for the confidence interval of 0.075, and then for the upper limit of the confidence interval, again the best estimate, but this time plus 2.58 for the 99% confidence multiplied by the standard deviation. So from this particular set of 10,000 sampled values, we are 99% confident that the p-value for our chi-squared statistic of 7.022 is in the range of 0.077 to 0.092.